Hello and welcome to Lesson 2.1, Inductive Reasoning and Conjecture. This is going to kick off Chapter 2 for us, which Chapter 2 is going to guide us towards our better understanding of logic and reason as it pertains to geometry and other parts of mathematics. So let's get started. All right, previously we've used data to find patterns and make predictions. We're going to do a lot more of that in this lesson, but we're also now going to make conjectures based on inductive reasoning. We're going to explain what those two things are, and then we're also going to find counterexamples. And these two objectives highlight your vocabulary for this lesson. First, we're going to talk about what inductive reasoning means, and then how to make a conjecture. Hopefully you've been able to do the reading and get this vocabulary written down in your vocab notebook, so this should be a review, but here it is. Inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. You're basing your statements, your logic, on specific examples, things that are measurable that you can use as an example to say why you believe something is the way you're saying it is. Conjecture, then, is a concluding statement reached that uses inductive reasoning. So whenever you make a statement like a prediction, or you're making a statement about the pattern as a conclusive type statement, you're making a conjecture. So let's take a look at example 1. We are going to write a conjecture, one of those conclusive statements, that describes this pattern, 2, 4, 12, 48, 20, 240. Then using that conjecture, we're going to find the next item in the sequence. So let's see if we can identify a pattern in this example. You'll notice we go from 2 to 4 to 12 to 48 to 240. So if I look at 2, then 4, then 12, then 48, and then 240, we could try adding numbers, we could try multiplying, dividing. We're getting bigger, so we're probably adding or multiplying. 2 plus 2 is 4. 4 plus 8 is 12. That's not really working. We make a big jump from 2 to 8. Then 12 to 48 is an even larger jump. And so it's probably not adding something. Since we're getting quite large quite quickly, let's take a look at what you can multiply by. 2 times 2 is 4. 4 times 3 is 12. 12 times 4 is 48, and 48 times 5 is what gives us 240. Well, you'll notice there's a much more distinctive pattern each time here. Each term is multiplied by the next consecutive integer in an increasing order. So the pattern we could notice is this. Okay, we're multiplying each term by the next consecutive integer. So our conjecture could be made like this. We could just restate that each term is multiplied by the next consecutive integer, or if you'll remember back to algebra, you might have talked about something called the nth term. Okay, there where this is the first term, that's the second, that's the third, fourth, and fifth, all the way out to the nth term, which we have as our unknown final term at the end. It just n represents that last term in a series like this, whenever the series kind of goes on forever. But n could be any one of these numbers depending on how long I make my sequence. Now, if n is the first term, then n is 1. Well, if I take 1 and I add 1 to it, I get 2. But if we're talking about the second term, if I take n as 2, n plus 1 then is 3, and that's what I multiply by to get 12. And if n is 3, then n plus 1 is 4, multiply by that 4 to get the next one. So we could say that our conjecture is that the nth term is multiplied by n plus 1, where you take the number in the sequence, you add 1 to that place in the sequence, not the number itself, not the term itself, but the number of the term, like the fifth term. I'm going to multiply 240 by 6, and if I multiply 240 by 6, my answer then is 1,440. All right, now you'll have another example that kind of applies that same kind of logic, example 2. We're going to talk about example 2 in class. So we're going to put a little star next to that one, and we'll come back to it in class when we've got some time on block day. And move on to example 3. Example 3, we're going to do the same kind of thing. We're going to write a conjecture describing this pattern and then use that conjecture to find the next number in that sequence. That's what we're looking for. So we want to start actually by looking for a pattern. Okay, why don't you pause the video if you need some more time, but look at that for a little bit and see if you can figure out what the pattern is here. Alright, after looking at that, we should see that the pattern is this. Every one of these numbers is a fraction. Even 1 can be written as the fraction 1 over 1, and the denominator of each fraction is what's changing. The numerator stays 1, but the denominator is increasing by perfect squares. That means each denominator is the next perfect square. Okay, so that can be our conjecture. Each new denominator is the next perfect square. And that means that our next term in the sequence would be 1 over 6 squared, which is 1 over 36. So the next term in your sequence is 1 over 36. Alright, why don't you take a look at example 4, read through that, and see if you can come up with a conjecture about this pattern and come up with the next term in the pattern. Pause the video to give yourself enough time to do this. Alright, when you look for a pattern, we should see the following pattern. Each one of these sets of circles, we are adding the next highest integer to. 1 plus 2 is 3. Then if I add 3 to 3, I get 6. If I add 4 to 6, I get 10. And so what do you think we're going to add for the next set? We're going to add another 5 to get 15 total circles, and they're arranged in a pyramid. Okay, so our conjecture could be this. Each term adds n plus 1 circles to the previous term, or to get the next term. So if n is 1, n plus 1 is 2. If n is 2, for the second term, 2 plus 1 is 3, so we're adding 3. If n is 3, 3 plus 1 is 4, we're adding 4 to get to the next one, and so on and so forth. So we know that our next item in our sequence is going to be a triangle of circles with 5 circles on the bottom, the 5 that we've added, to the previous set of circles. And it doesn't have to be perfect, but that is what your next step should look like. Alright, for example 5, we're going to make a connection to algebra by making a conjecture about some expressions involving numbers and their addition, subtraction, things like that. So here's what it says. Make a conjecture about the sum of an odd number and an even number. So what we need to do is list some examples of taking the sum, means we're adding, of an odd number and even number. Let's take a look at the first odd number, 1, the first even number, 2. 1 plus 2 is 3. Well, let's try another odd and even number like odd number 3, even number 4. 3 plus 4, that's 7. Let's try another one. Let's try an odd number 11 plus an even number 4. Well, that's 15. Notice that all of these results are giving me odd numbers. And you could carry this out with as many examples as you want, and the pattern is that an odd number plus an even number will always give you a sum that is odd. So here's our conjecture. The sum of an odd number and an even number is odd. And that can be our conjecture. Alright, for examples 6 and 7, those are two more that we're going to cover in class, so just put a star by those and we'll come back to those during class time. And I do want to talk quickly about the last couple examples here, which use the concept of a counterexample. A counterexample, in short, is just an example that proves that a conjecture or statement is false. So let's take a look at example 8. In example 8, you need to be able to find a counterexample that shows why each of these conjectures is false. So first statement, if n is a real number, so if this variable n represents any real number, then n squared is greater than n. We just need to find a value for n that makes this not true. Well, there's many different ones we could use, but if we say if n equals 1, 1 squared is 1, and 1 on the other side, those are equal, not greater than. So n squared is not greater than n. N squared equals n. So this is our counterexample, because when n is 1, that makes this statement false. Part B, if jk equals kl, then k is the midpoint of segment, that should actually say jl, just a typo. Okay, well that works if they're collinear, but that never says they're collinear. We could come up with a situation where there's point K, there's point J, and there's point L, and these are congruent segments, so those are equal, but K is not the midpoint because they're not collinear. So there's a counterexample. Lastly, every pair of supplementary angles include one obtuse angle. Well, that works almost all the time except for one counterexample. Supplementary angles, remember, add up to 90 degree or 180 degrees. But if those both happen to be right angles, well, they're supplementary, but neither of them are obtuse. So if they look like this, there's angle 1, and maybe there's angle 2. They're both 90, so they're supplementary. When you add them together, they get 90, but neither one is obtuse. So there's your counterexample for example 8. All right, example 9 is another one that we're going to cover in class, so we're not going to take time in the video for this. If you want to try any of these examples that we've skipped on your own and see if you can come up with answers, then we can check them. There's nothing wrong with that, and otherwise we will finish these examples in class and get more work on lesson 2.1 over inductive reasoning and conjectures.